For systematic simplification of Boolean expression using K-maps, we need to introduce some of the terminologies used. For instance, first one is called prime implicant. A prime implicant in a K-map will be a product term obtained by combining the maximum possible number of adjacent squares into a rectangle with a number of squares of a power of 2. Okay, either 1, 2, 4, 8, 16. We call prime implicant as an essential prime implicant if it's the only prime implicant that covers or includes one or more minterms. So we have prime implicant, and then essential prime implicant. And prime implicants and essential prime implicants can be determined by inspection of a K-map. Okay, we will see it shortly. A set of prime implicants covers all minterms if for each minterm of the function at least one prime implicant in the set of prime implicants includes a minterm. Let's see. Here, given the following K-map, right, we now want to show where prime implicant and then essential prime implicants are. For instance, the first prime implicant is following, right? We said that prime implicant is a product term, which is obtained by combining the maximum possible number of adjacent cells, which contains one in the map, into rectangular with the power of 2. So BD is a prime implicant. Next one, C. Okay, this one, right? Okay, CD. So BD after simplification. CD for the following group of 4. This is also prime implicant, maximum possible grouping. Another prime implicant, right? And another prime implicant can be obtained here, A, not B. Also, these two are also considered as a prime implicant, right? And 4 adjacent, right, cells that are located here are also grouped together, so also form the prime implicant. Now, what is the essential prime implicant? Among these, which one of them are essential prime implicant? Right? We said prime implicant is called an essential prime implicant if it is the only prime implicant that covers one or more minterms. For instance, this is again the same map, Karnaugh map, and we need to find the ones. So according to the definition, so we have one here that cannot be grouped with any other possible, let's say, grouping of prime implicant. So this one is left alone, this one. And also second essential prime implicant is BD, because one of the minterm cannot be covered or combined with others at the maximum. So BD, then not B, not D are those essential prime implicants. If you look at other ones, you can see that they can be covered with other grouping, right? Twice. Only this one and this one cell cannot be overlapping with other grouping. So they're called as essential prime implicant. Now let's take a look at the following function, Boolean expression, and then try to find all prime implicants. So first I'll draw the K-map again. Okay. Now we have A, B, right, and then C, D variables. 1, 0, 1, 2, 3, location of those. 6, 7, 12, okay, 13, 14, 15, okay, I should have started from here, 8, 9, 10, 11. Now I just plug in those values whenever they're 1, 2, 3, 8, 9, 10, 11, 12, 13, 14, 15. Right. Yeah. Now we need to apply grouping. So we need to first find the prime implicants. So let me try to find this one, this one, this one, this one as one group, right? That's one grouping. And second grouping could be the following group of 8. And next the grouping is the following, right? Next maximum possible grouping. So we have, let me call it first group, and then this grouping as second group, and this one is as third group. Actually here we could combine it differently. We could group the following 4 differently. The term 3, okay, let me find this adjacency, right? The following. If we apply simplification, then f will be equal to, for the term 1, we will obtain a, and then for the second term, we will obtain not b, not d. And for the third term, we will obtain, okay, not b, b doesn't change, and then c. Right? This is the formula. Now the question was about finding all the prime implicants. If you recall, the definition of the prime implicant is a product term obtained by combining the maximum possible, right, number of adjacent squares in the map into a rectangular. So all of these terms are product terms. All of these, right, groupings are prime implicants. So first grouping, now first was this one, right, and second grouping, and then third grouping. All of them are actually the prime implicants in this case. Here we have another example. We have a function g defined by the following sum of min terms. I will leave this example as an exercise to you. You should find 7 prime implicants. Once you draw the map of Karnaugh Map, and then apply grouping, and then you should be able to find 7 prime implicants, as we just did in the previous example. We have seen the 4 variable K-maps. Can we extend K-maps to 5 variable or more? For instance, for 5 variable problems, we can use 2 adjacent K-maps. We use 2 K-maps, right? As it becomes harder to visualize adjacent min terms for selecting prime implicants. And for we can extend the problem to 6 variables by using 4 K-maps, right? 4 K-maps of 4 variables. So here, if you have w, x, y, z, and then v, 5 variables, then we'll have 2 cases where v will be 0, and then where v will be 1, right? That's the way we can extend the K-map into 5 variables. For instance, let me show this the following example. This is the example of 5 variable K-map or overlay. Look, A, B, C, D, E. Well, A, B remains 0, 0, 0, 1, 1, 1, 1, 0. Only here C changes, look, so 0, 0, 0, 0. In this case, in this 4 variable 4x4 cell, C remains 0. And then in this case, C changes to 1, 1, 1, 1, 1. So we can separate 5 variable K-map using 2 4 variable K-map. And in this case, C will be in one case 0, and in another case, C will be 1. And for 6 variable, we'll have 4 tables, 4 K-maps. One of the very useful concepts in simplifying the output expression using the K-map is the concept of don't cares. These don't care conditions in K-map will allow us to replace empty cell of a K-map so that we can form a group of the variable which is larger than forming groups without don't cares. For instance, a function table or map may contain entries which it is known the input values for the min term will never occur. or the output value for the minterm is not used. Okay, so these cases can be considered as don't cares in the K-map cell. Okay, because the output value need not be defined. Instead, the output value is defined as don't care. And also we can use these don't care conditions or the cells in the K-map as X and then form a group of cells which is larger, right? We said that if we group cells by forming larger groups, then the Boolean expression can be further simplified, which is directly connected to the cost of the logic circuit, which will be less, right? So look, in this simple example, a logic function having the binary code for the BCD, binary coded digits, as inputs, only the codes we use is range from 0 to 9, right? And then the other 6 code that range from 10 to 15 is not used. So the output values for this BCD case can be considered as X, as don't care, and we can use them in our group, okay, when we group the cell of minterms. Let's take a look at this example. We have a circuit with two distinct set of input variables. On one set is A, B, C, which can take on all possible combinations, and another set of input is Y, which takes on only values of 1 and 0. Okay, 0 and 1. And we have a single output Z. Okay, so our circuit is represented by a function Z, which has A, B, C, and then Y, right? And then, look, the circuit that receives the output Z observes it only for combinations of A, B, C, such that A is equal to 1, B is equal to 1, and C is equal to 0. Otherwise, ignore all other inputs. Okay, so only for these specific combinations, circuit is defined to be followed, and then for all others, it's ignored. And Z, which is specified only for those combinations and for all other combinations of A, B, and C, we can call it as don't care. Okay, our function or circuit doesn't care all other combinations. For instance, Z, if we specify Z for A, B to be true, like 1, 1, and then C complement to be 1, these are the location of minterm. And all other possible inputs will be considered as don't care. For instance, this function will be corresponding to the don't care conditions, right? And look, each don't care can be, we said, labeled as X, and can take either 0 or 1, okay, depending on whether you're working with sum of products or product of sum, right? If you're working with sum of products, you may want to label X as zeros or ones as product of sums, or vice versa. And also note that any minterm with value X need not be covered by a prime implicant. That is one condition. So again, we can use don't cares while forming groups of cells. Okay, we can consider this don't care cell as 1 or 0, or we can also ignore that cell. Therefore, don't care condition can help us to form a larger group of cells, which will reduce the circuit cost or the expression. Here we have another example. So binary coded decimal function, which represent 5 or more, right? So 5 or more decimals. So if you look at this 4 variable K-map, here we have the function of W, X, Y, Z, which is again defined as 5 or more, 5, 6, 7, 8, 9, right? And the location of the don't cares are labeled as X here. Okay, we said in binary coded decimal, the values above 9 is not used, 10, 11, 12, 13, 15, right? 14, they're not used. But we can use them to form a larger group of ones so that we can minimize the expression, F1 expression. Right here we are using these 2 more to form group of four, two more don't cares, okay, to form a group of another four, and here we are even using 6 don't cares to form the group of 8, right, ones. And also in terms of the cost gates, look, F1, when we use don't care, we will have the following three terms, W, X, Z, X, Y. The gate input cost here will be equal to 7, which is much lower in cost than, let's say, F2. F2, if we group only these without don't cares, using the don't cares, then we will have the following variables, right? The terms, right? Some products. And the gate input cost is 12. So don't cares allow us to form the group, larger group of ones in K-map, right? Well, these location of these cells are again the output values of the functions, right? If you just think about this as a truth table, right? In truth table, the function, the BCD, okay, whatever outside, let's say above the 9 will be not considered in BCD, right? So 10, 11, for example, up to 15. But we can use those values in our K-map. Now let's take a look at the following sum example. So we want to find the optimum product of some solutions for the given function, for the following function, of 4 variables defined by A, B, C, D. And we have the following minterm locations and then don't care conditions. Right? So these are all the indexes of minterm. And then don't care, as we said, it will be the condition where the function's output is, we don't care about the function's output for these specific inputs. Okay? So we don't use function's output. So to solve this problem, the optimization problem, let's say, or simplification using K-map, we form the 4x4 K-map and form the grouping of the cells at these locations and include our don't care conditions, X1s. For this example, I will use an online tool as a demonstration as well that you can also use. We know how to solve a K-map using by hand, right? There are also some softwares available. Let me show how to do one of them. For example, this is one of the websites that you can use. So 332x8.com, okay? This website allows you to use the Karnaugh Map online. Here, I just opened the 4 variable truth table for our example ABCD, and the output is here defined by Y, not F. And I already indicated the location of the minterms, okay, defined in our function, and then don't cares. We want to find the POS, product of sums. So if I just submit these, then we will see the product of sums. Here we are interested in, let's say, the maximums, the opposite zeros, right? So will be identified by 0. Yeah, because again, we are interested in product of sums, we will start grouping zeros, not ones. Ones are location of the minterms, the zeros are location of the max terms. So in this case, yeah, X are the location of the don't care conditions, as we discussed. 3 don't care ones. And then we can change them, we can treat them as 1 or 0, right? Because we're interested in POS, then we can treat them as 0, so that we can form the group of the following. So 0, 2, okay, here, these 4 zeros, okay? And then, which will give us B, not B, and not D. And then we will use these X, or don't cares, to form the second largest group of 4, right? And then 5, 6, and then 7. Here we are using these 2 don't cares, which will give us not A and then B. Okay, here this is the complement of our function, which will give us following. And then if you apply another complement of function, then we will get the product of sums. This is sum of products. And also the website shows us how we can, we can take a look at the circuit, okay, implementation of the following expression. And this is the truth table, right? These are the location of min terms and don't care conditions. Check out this website and then experiment more, and it is very useful. We have studied the K-map so far and have seen several examples how we can perform optimization using the K-map, and now we have the don't cares as well. So there are some specific set of steps recommended as follows for optimization algorithm. First, we find all prime implicants. Okay. Second, we include all essential prime implicants in the solution, and then we can select the minimum cost set of non-essential prime implicants to cover all min terms, which is not covered yet. Then we can have two different solutions. So first, if you want to find the optimum solution, okay, if you want to obtain a good simplified solution. So there are two different objectives, let's say. So on obtaining the optimum solution, we can read more on optimization, reading supplement of the textbook. But now let's take a look at this good simplified solution case. We want to use a selection rule. The selection rule is very simple. So it's based on prime implicant selection. So here we want to minimize the overlap among prime implicants as much as possible in prime implicant selection. In particular, in the final solution, we will need to make sure that each prime implicant selected includes at least one min term, not included in any other prime implicant selected. Let's see in this example. So here we have the K-map of 4 variables, right, defined by 1, and we know that any possible largest grouping, okay, are prime implicants. And then essential prime implicant definition is there are some ones that cannot be grouped with any other adjacent cells grouping, right? So in this case, we find all prime implicants and essential prime implicants. On this example, there is some overlap among prime implicants. So we want to minimize any overlap among all prime implicants as much as possible, right? And then we want to make sure that each prime implicant selected includes at least one min term, which is not included in any other prime implicant which is selected. In this example, we are using the don't cares. Okay, here we have some overlap between this prime implicant, and all of them. But in this case, these are the prime implicants without overlap, including don't cares, right? We are using don't cares to form the maximum grouping.